Today, we're diving into an idea that sounds like it's straight out of a movie, but is actually at the very cutting edge of physics. It's a question that could change everything we think we know about reality. Think about it. The world around us, it feels so smooth, right? So continuous. But what if that's just an illusion? What if, when you zoom all the way down to the smallest possible scale, space and time are actually made of tiny, indivisible units, like pixels on a screen? It's a wild idea, but it runs headfirst into one of the most sacred rules in all of physics. So to really get why this is such a huge problem, we first have to understand the rule. And this isn't just any rule. This is pretty much the foundation that all of modern physics is built on. It's called Lorentz symmetry. And what it means is that whether you're standing perfectly still or zipping through space on a rocket at a constant speed, the laws of physics look exactly the same to you. The most famous part of this, the part everyone knows, is that the speed of light in a vacuum is the universe's ultimate speed limit. It's the same for everybody, no matter how fast you're moving. And look, this isn't some minor detail we can just brush aside. Lorentz symmetry is what keeps the universe making sense. It's what guarantees that a cause always comes before its effect. If you break this rule, you could see a glass shatter before you drop it. It completely destroys logic. It's the absolute bedrock of Einstein's relativity, of quantum mechanics, everything. So breaking it would mean our entire understanding of the universe is just wrong. Okay, so we've got our golden rule. It's unbreakable. Now let's see why this elegant, simple idea of a pixelated universe just completely smashes into it. The conflict really comes down to a clash of textures, if you will. Lorentz symmetry demands a perfectly smooth reality, where you can turn at any tiny angle or move at any tiny difference in speed. But a universe made of pixels? That's a rigid grid. It's clunky. It has built-in directions and minimum steps you can take. They just don't mix. Let's make this really concrete. Just imagine a simple square grid, like a checkerboard. A particle moves 1 pixel to the side in 1 tick of time. Its speed is, let's say, 1. But what if it moves to the nearest diagonal pixel? Well, thanks to Pythagoras, we know that distance is the square root of 2, about 1.41. It traveled a longer distance in the same amount of time. Its speed is different. All of a sudden, the speed of light would depend on which direction you're going. And that's a catastrophic failure of Lorentz symmetry. So you'd think, okay, that's it. Game over for the pixel idea, right? It seems like a fatal blow. But physicists are a stubborn bunch. They didn't just give up. Instead, they started this incredible hunt for a way to build a pixelated universe that doesn't break the golden rule. So the first clever thought is, okay, the square grid has preferred directions, the up, down, and left, right axes. What if we use a grid that's the same in every direction? Enter the polar grid. You know, a central point with circles spreading out. It seems perfect. It's perfectly symmetrical when you rotate it. All directions are equal. Problem solved, right? Well, not quite. What we've really done here is trade one problem for another, arguably worse one. See, the square grid is homogeneous, which is a fancy way of saying no point is special. The grid looks the same everywhere. But it isn't isotropic. Directions are different. The polar grid, it's perfectly isotropic, which is great, but it's not homogeneous at all. It has one very special point, the center. And having a center of the universe is a much, much bigger sin in physics. The idea that the laws of physics are the same everywhere is even more fundamental. So the polar grid, while it's a neat idea, is the complete non-starter. This leads to the next brilliant idea. What if the grid isn't just a passive stage? What if space itself is an active, dynamic thing? Imagine a particle moving through this field of pixels, and as it moves, the pixels around it kind of warp and rearrange themselves to smooth things out. But this idea hits a wall too. For one, a particle moving through this rippling grid would constantly be creating these little waves in space, which would sap its energy. It would slow down all by itself, which violates inertia. The diagonal problem doesn't really go away either. And here's the kicker. For the grid to react to the particle's motion, that information has to travel. And it can't travel instantly. That would break causality. So it's another dead end. It really seems like we're stuck.
Every single attempt to build a pixelated universe has failed spectacularly. But this is where the story takes a radical, truly mind-bending turn. The solution, it turns out, isn't to fix the grid. The solution is to completely rethink what reality even is.
This quote gets right to the heart of the breakthrough. What if there isn't one single objective grid for the whole universe? What if the correct version of reality is something that's defined locally, for you, right where you are?
This exposes the hidden assumption we've had this whole time, that there has to be one true grid, one objective reality that we all share. The radical new idea is to just let that go. What if every single observer experiences their own perfectly valid local version of reality, and that's just how it works? The best way to picture this is the balloon analogy. It's just brilliant. Imagine you're a tiny ant living on the surface of a balloon. Right where you're standing, the surface looks perfectly flat. That's your local, correct reality. As you walk around, that patch of flatness moves with you. Now, from your perspective, far-off parts of the balloon look stretched and distorted. But here's the magic. Any signal coming from those distorted regions has to travel across that stretched surface to get to you. And that journey corrects the signal, so by the time it arrives, it obeys your local rules perfectly. And this leads to this incredible realization. Trying to force a single objective grid on the whole universe is like trying to make a flat map of the Earth. You're always going to get weird distortions and paradoxes, like Greenland looking bigger than Africa. The solution isn't to make a better map. The solution is to accept you live on a globe. You can only ever see your local patch, but it's perfect. The problem wasn't reality. It was our insistence on a flat map. So, we have this stunning, mind-blowing, philosophical solution. It looks like we've saved the pixelated universe. But as it so often happens in physics, solving the conceptual puzzle just reveals an even bigger, harder challenge. You see, having a brilliant, elegant concept is one thing. But physics isn't just about beautiful ideas. A concept isn't a theory. A theory needs math. It needs to make precise, testable predictions. And that is the billion-dollar question right now. Can anyone actually write down the equations for this bizarre, relative, dynamic grid? Can you build a mathematical model that shows how all of our individual, local realities combine to produce the smooth, continuous universe that Einstein's relativity describes so perfectly? The honest answer is no one has done it yet. The problem has transformed. It's no longer seen as impossible in principle, but it is completely unproven in practice. This is the absolute frontier of physics. And this brings us to our final thought, the real takeaway from all of this. The quest to figure out if the universe is made of pixels has led us to a far deeper and more profound question. Is reality a fixed stage, an objective thing that we all share? Or is it something far more personal, a story that the universe tells uniquely to each and every one of us?